Welcome. In this video, I'll be covering the topic of ions and salts, along with the information and methods used to solve different kinds of problems you'll be facing when working with ions and salts. So, what is an ion? In short, the definition of ion is an atom or molecule with a charge. This charge is obtained by the molecule having either lost or gained a number of electrons, but the amount gained or lost must not be the same for it to be an ion, resulting in the molecule being charged due to having an unequal number of electrons and protons. The way to denote charge is by writing it at the top right end of the molecular formula of a chemical with a plus, meaning the molecule has a positive charge and has lost an electron, whereas a minus means it has a negative charge and has gained an electron. In front of the plus or minus, a number might be written to denote how many electrons have been gained or lost if it's more than one. Some chemicals can have multiple charges such as iron. When in their ion form, it's noted by their charge, but when it becomes part of a salt, it'll be written with the previous charge in parentheses. When it comes to ionic compounds, the simple definition is that an ionic compound is a compound which is comprised of one or more cations and one or more anions. However, the cation and anions must be present in such a way that their charge cancel each other out, making the overall ionic compound neutral. A quick note to add is that the term salt and ionic compound can be used interchangeably with one another. Lastly, it's important to note that when writing the name of a salt, the name of the cation is always written before the name of the anion. Now, let's look at ionic bonds. Ionic bonds are simply put bonds between ions. These bonds are created by an atom giving away one or more of its electrons to another atom, thereby becoming a cation, whereas the atom which received the electrons becomes an anion. The amount of electrons that given or taken is determined by how many electrons an atom needs to mimic the electron shell of the nearest noble gas in order to become more stable. For example, chloride's nearest noble gas is argon. If we look at their electron shells, we can see that the only difference is that chloride has one less electron in its outermost shell. This means that chloride will want to find an electron to put in its outermost shell and thereby become a chloride ion with a charge of -1 and also create an ionic bond with a cation. Furthermore, in order to create an ionic bond between two atoms, they must have an electronegativity difference of roughly 2 in order for it to be an ionic bond. That being said, however, it's more of a rule of thumb than a rule set in stone. A useful skill to develop when working with salts and ions is being able to predict what salts will be created from a reaction between different ions or atoms. The first step in this process is to look at what charge the ions have. If you look at ions creating a salt, the charge will be given next to the element symbols as explained earlier. The next step is to then find out what ratio the two ions should be present in the salt, i.e. the chemical formula of the salt. If we, for example, have our cation be a magnesium ion, which have a charge of 2 plus, and our anion being a phosphate ion, which have a charge of 3 minus, these ions will react to create magnesium phosphate. The next step is to write these ions as if they're already in the same salt, but kept their charge. Now we'll then look at the charge. The first thing to check if it's the value of the charges are the same, ignoring the minus and plus. And since we know that 2 and 3 are in the same number, we can see that they don't react 1 to 1. If they did have the same charge, then the reaction would already have been balanced and we would know the chemical formula of the salt. Now then, the second step is to use the crisscross method. The crisscross method is extremely simple. What you do is you take the charge from the cation and move down to the bottom right of the anion, removing the charge. And now you do the same for the anion and take the charge of the anion and move it down to the bottom right of the cation, removing the charge once again. We then have parentheses around the phosphate to separate 4 and 2. If you want to, you can then afterwards check if the charge cancel each other out, and in this case we can see that they do. Since we have 3 magnesium with a charge of +2 and 2 phosphate with a charge of -3, which both equal +6 and -6 respectively, we can then see that if we add them together, they cancel each other out and become 0, i.e. neutral, and thereby our salt is neutrally charged as it should be. When working with ions, there will be some times where the charge isn't given in a problem. In that case, you'll have to know them. Luckily, there's a method which you can use to predict the charge of at least a good chunk of the ions you'll be working with. This method involves looking at a periodic table. The one currently on screen is from ptable.com, which I'll leave a link to in the description down below. Now, as you can see, I have written some Roman numerals over a few of the groups. These groups are called primary groups. What makes them useful is that all the atoms in group 1 has a charge of plus 1. All the atoms in group 2 have a charge of plus 2. All the atoms in group 3 have a charge of plus 3. All the atoms in group 4 have either a charge of plus 4 or minus 4, but you likely won't be using them, so there's not much need to focus on them. The atoms in group 5 have a charge of negative 3, the atoms in group 6 have a charge of negative 2, and group 7 has a charge of minus 1. Lastly, group 8 never forms ions but are noble gases, which is what the other atoms want to look like, as explained earlier during the topic of ionic bonds. Solubility in chemistry is often taught under the subject of equilibrium. However, it does make an appearance when talking about ions and salt, however in a much simpler form. For now, when looking at solubility, you'll just be asking yourself whether the salt in question is soluble or not. For this, you can look at a salt solubility chart such as shown on screen. The S means that the salt will be dissolved in water, i.e. the salt is soluble, and the I means it will barely if at all be dissolved, i.e. the salt is insoluble. There is a little note regarding the solubility of salts because they're only soluble until a certain point. If you keep adding salts to a solution, it will eventually become saturated. When a solution saturates, it means that it has reached a point where the salt you add won't be dissolved, but rather fall to the bottom of the solution in its solid state. Lastly, when a soluble salt is put into water and dissolved, we don't write it as the salt is dissolved in water, but rather that the individual ions are dissolved in water. This becomes important if you have more than one salt in water and some of the ions react with each other to form an insoluble salt, such as seen on screen here. While the second step is typically optional and it's your own choice if you write it or not, the last one isn't. Moreover, the ions that remain dissolved are referred to as spectator ions. You can predict which ions form soluble or insoluble salts by looking at the solubility chart shown earlier. That's all for today. Please be aware that if you want help solving the problems you'll face when working with solid ions, then a video about just that can be found in the icon in the top right corner and in the description down below. And as always, feel free to like and subscribe, feedback, questions or suggestions down in the comments below, and as always, have a nice day and good luck with your work.